consider that being not in the correct order.
Question.
Yeah.
You're supposed to be sharing your screen right now, right?
Oh man. Thank you.
You're all good.
That'd probably be helpful.
You do that every meeting. So long, it takes 3 months.
Yeah, just see everyone's paying attention.
Yourself as well, too.
Just telepathically communicate. I want to do the whole screen.
I'll check this.
Okay, now you should be able to see my screen. So valid parentheses. I can read through, I'll just read through it quickly again. So we already heard everything. So given a string S containing just these characters, we want to determine if the input string is valid. And it's valid if open brackets are closed by the same type of brackets and open brackets are closed in the correct order. And every closed bracket has a corresponding open bracket of the same type. So you can see here, this is considered a valid string. And you can see all of these are in the correct order and they all have a corresponding opening and closing bracket. So that is also a valid string. And here, this opening bracket does not have a closing bracket. And this closing bracket also doesn't have an opening bracket, the corresponding opening bracket. So it's considered an incorrect string and we return false. So for this, I use 2 data structures. One is a hash map that just maps closing brackets to opening brackets. And then I also use a stack. And so I push every opening bracket onto the stack. And then in here, I'm checking if the current bracket that we're looking at is a closing bracket. If it is, then we check if the stack has an element in it. And if the element at the top of the stack is a corresponding opening bracket to the current closing bracket that we're looking at, then we're going to remove it from the stack because it's a valid pair that we found. And then otherwise, if the stack doesn't exist or we don't have a matching opening bracket in the stack, then we return false because that would be like in this case, we don't have a valid match. And then otherwise, we're just appending every opening bracket onto the stack. And then this is an edge case down here. We're checking if there are no more opening brackets in the stack. That means that we've found a matching closing bracket for each opening bracket. So then we return true. Otherwise, we return false because that means there's still an opening bracket in the stack that we haven't found a closing bracket for. And that's it. Any questions? Anyone else do this a little differently than me?
I did actually. So when I did a job, so that's all different. Actually, looking for the craziest one line meeting. Nah. I was just wondering is I don't even know how to check the printout, but I wonder if you could just do like if the characters are I guess it would go discussion posted in. I wonder if you could just do like if character is equal to this -1, like if they're like right next to each other in the
I see.
charts.
Yeah.
So if you could just do that rather than using a hash map or like I just did a function. I should use the switch to be honest.
Oh, really? That's it.
I should have probably done a switch would have been slightly better than that. Because I don't know, I don't actually know if you can visualize a hash map in Java like you did.
Yeah, I don't know if you can either.
So I kind of forgot what I did, but obviously I did a little bit different.
So I'm just a tad different. So yep,
I'm pushing. But that just checks if it's like a closing, it's the closing bracket. But I pushed on in the loop and then it was empty and at the end it was good.
okay. Yeah. Yes. This is just where you make sure that there's a corresponding match.
That's the what your hash map.
I see. Okay, that's nice.
And B closes A, yeah.
Yeah, I don't know if you can define a hash map like that in Java.
I mean, you could always, it would just be what would that be, 3-4 liner
Yeah.
initialize and then add the 3.
Yeah, that's
I know you could- I think probably not.
Why not?
I mean, you can do some things in Java that are kind of Python like, you can. But I don't know if you'd be able to do that though. You should Python, it's better.
Uh-huh. Python is superior.
Yeah, if you want to run slow programs, then
Oh, shit.
I shouldn't say shit saying I'm using Java.
I can show my solution. It might be a little bit simpler.
Ryan's got the one.
Yeah, let's see, Ryan. Got the one-liner.
No.
Come on.
Do you want me to share my screen or just send you the? I'll just send it to you. Make it a little bit easier. Yeah. So essentially how it works is it'll loop through every character in the string that's passed in. And if the character being passed in is an opening parentheses or an opening bracket or an opening curly bracket, it'll push that corresponding bracket to the stack. And then it'll check, right? So if it's like for, let's say like test case 2, right? It'll push the parenthesis, the opening parenthesis. And then on the second iteration, it'll go through again. It won't find an opening bracket, and then it'll go to the final else if, where it'll just make sure the stack isn't empty, and then it'll do stack.pop. And if this value is not equal to C, so the closing bracket, it's basically checking like closing bracket to closing bracket and making sure that the two values are the same. So in the event that it's an opening and a closing bracket next to each other, it'll just be comparing closing bracket to closing bracket instead of opening bracket to close it, if that makes sense. That's just kind of how I thought about it.
Yeah, nice. That makes sense. I see how that would work. So you're essentially pushing the opposite.
Yeah, if you just push the opposite and then compare the two values, you'll be able to tell very easily if it's truly in the correct order or if it's not.
Nice. Cool. That's cool to see that done a couple of different ways. Nice. All right. Anyone else want to share any solutions or questions? Well, let's move on to number 2, baseball game. So you are keeping the scores for a baseball game with strange rules. At the beginning of the game, you start with an empty record, and you're given a list of strings operations, where operations I is the ith operation you must apply to the record, and it is one of the following. If it's an integer x, then we record a new score of x. If it is a plus sign, then we return a new score that is the sum of the previous 2 scores. If it's a capital D, we record a new score that is the double of the previous score. And capital C, then we invalidate the previous score, removing it from the record. So after we performed all of these operations in operations, then we want to return the sum of all the scores on the record after applying all of them. Okay, and luckily all our operations are valid, so we won't have to make a check for that. That's nice. And so for this test case, we start off with 5. So we add it, we record it. Then 2, we record that as well. And then we're past C. C invalidates the previous score. So we're going to remove 2 from our record. So now our record only consists of 5. Then we're past D, which is record a new score that's a double of the previous score. So now we're going to record 10. So now our record consists of 5 and 10. And then our next one is plus, which records a new score that is the sum of the previous 2 scores. Hey, how's it going? So our record has 5 and 10 in it. Wait, is that right? I lost my train of thought.
Yeah.
Yeah, 5 and 10. Then we're past the plus sign. So then we record a new score that is a sum of the previous two. The previous two being 5 and 10. So we record a new score of 15. And then at the end of that, we add up all of the scores that are in our record, and that sums up to 30. So for this, I used a stack. And then for each operation in operations, I have these this if statement here that basically checks if it's a plus sign, a D, a C, and then otherwise we're just gonna append it onto our stack, which is the same as recording a new score. So if we have a plus sign, then I get the previous two scores, previous one and previous two, by looking at the top two elements of the stack. And then I record the sum of these. And after I record the sum, then I append a new value, which is the previous sum to the stack. Otherwise, if our operation is D, then I'm going to double the top of the stack and append that to our stack as a new element. Otherwise, if our operation is C, then I invalidate the previous score and remove it from the record by just popping from the top of the stack. And at the end of that, I just return the sum of whatever is left in the stack, which should just be integers. That's it. Any questions? Any different ways of doing this?
I used a switch.
Oh, really? Switch case statement. Nice.
I did exactly the same order.
Pretty much. Yeah, there's not too many different ways to do this one. I feel like it's all pretty much the same. Okay.
I could share mine. I think I did it slightly different.
Maybe. Let's
Maybe
see it. Yeah.
I'm just looking at yours over again to make sure I'm not sharing the same answer twice. But yeah, I'm pretty sure it's different. If it's not, then
No big deal.
oh well. I put some comments in this one this time, so maybe it's a little easier to understand. And it's Java too, so yeah.
Okay.
Yeah, so essentially, we loop through the entire string array operations, and then each time we go through, we'll check. It's very similar to a switch, where we check if the value is equal to something. One of the cases I ran through when like figuring out this problem was I noticed that you can push in kind of any number, like it could be a 5 and a 10 or a 20. And there's no way to really, check like, hey, how do I, I can't do basically if s dot equals, any number like I did with the plus sign or the C or the D. So I found that if you just put that at the bottom where in the final else statement, basically if it makes it all the way through without getting stopped, basically it's not a D, it's not a C, it's not a plus sign, then it must be a number. So that was one of the things that I got around. And essentially it's pretty much the same thing that you did. Calculate the values needed. And then the only thing I think I did slightly different is here at the bottom with the while statement, where I just kept track of the total and just returned it. So I just instantiated an integer variable at 0, and then just stack popped every value and added it to the total and then just returned it. So I took all the remaining values and then just added it up and returned it.
Nice. Yeah, it looks good, man. Yeah, so in Java, you can't just like call a sum of stack or whatever, right? You'd have to iterate through it like this, wouldn't you?
Yeah.
And think of
And add it up.
Yeah.
There might be a sum in that, but I'm gonna Excel that.
At least not that I know of.
Inferior language again. Nice, looks good. Sweet. Awesome. Oh, for time complexity, so both of these solutions would be linear, so they both be O of n, where n is the number of operations in our string array. And then space complexity would also be O of n, because we could store each operation in the stack possibly. All right, let's go on to the next one.
The temperatures was a bit tricky. I wasn't able to solve it, actually. I had to use help.
Yeah, I think the first time I did this one, I had to look it up as well.
And first time I really interacted with this design paradigm.
Yeah, the monotonic stack is interesting, isn't it?
Yeah. So, but I got better at it. Yeah, I think, yeah, it was on the blitz we went over. I weeded the meteor. That was helpful.
Yeah, that's right. Yeah, they're kind of similar once you get like the hang of that.
Yeah, once I figured out like the
Yeah,
thought process, I was like, oh, that makes sense.
yeah, exactly. All right, daily temperatures. So given an array of integers temperatures, which represents the daily temperatures, return an array answer such that answer I is the number of days you have to wait after the ith day to get a warmer temperature. If there's no future day for which this is possible, keep answer I equal to 0 instead. Realize I used to have a bunch of gibberish from when I was testing. Let me get rid of that. There we go. Okay, so here's our input temperatures, and here's our output, which is a res array. And you'll see that each of these corresponds to the number of days we had to wait for the temperature at the ith day to increase. So for 73, we only have to wait 1 day for the temperature to increase. So in the position I, which is 0 for 73, we insert a 1 into the res array. For 74, it takes 1 day for the temperature to increase. So again, we insert 1. For 75, however, it takes 1, 2, 3, 4 days for the temperature to increase. So then we insert a 4 in our res array, and so on. And then, important edge case to notice is for temperatures where we never find an increased temperature, then we just append 0 to our res array. So you can see here is my stack, and then I started off my res array by initializing it with zeros. So for the length of temperatures, that's how many zeros we're going to have in my res array, and that takes care of the case for if we never find a future day where the temperature increases. By default, we're just going to have 0 in our res array. And then for index and temperature in our temperatures array, while we have found a temperature that is greater than the top of the stack, then I'm going to pop the less than temperature from the stack. And I find what I'm storing in the stack actually is a tuple containing the index and then the actual temperature value of each temperature. And then, so when I pop from the stack, I receive this tuple containing an index and a temperature. And then what I do here is I access the index by using prev 0, which is the index in this tuple. So at res, in the index of the corresponding temperature, I calculate the amount of days it took using the 2 indices here for the temperature to increase. So this will continue calling while we're currently at a temperature that is greater than the top of the stack. And then once we are no longer at a temperature that's greater than the top of the stack, we go ahead and append the current value and its index to the stack inside of the tuple. And at the end, I just return res, and that's it. All right. Any questions? Anyone else do it differently? Sweet. All right. Oh, for time complexity, this is going to be linear. It's be O of n, where n is the number of temperatures and temperatures. And then also of n for space, because we're storing temperatures in our stack. Okay. Now this was the optional hard. How many people did this one? I actually didn't do this one. Nice, Mitchell. Looks like only Mitchell. Nice.
So this one, I mean, if you all just post it on, I guess, back in discussion. So this one is actually give it a marker. Look, it's
Oh, yeah.
we're explaining. Well, there's one in there.
Here. Oh, nice, fine.
So, I don't know, right here, this kind of main camera.
Yeah, let me turn the camera on.
Yeah, so this problem is, or at least how I solved it, is very much based off of the previous problem. So the previous problem gets the next greatest value in the list. However, I want to flip this, how I flipped it around, and I did get the next smaller, the next value that's smaller than it, or the next index that's smaller than it. So, and so I do that, and so I go through it both upwards, so the next smallest and the previous smallest for everyone. So I have two arrays or two outputs that I'm storing this in. So basically, if we have, or I suppose I should put the problem actually. They're basically trying, we're trying to get to the biggest rectangle, right? Out of these of this rectangles, and as you can see here, we have 2, 1. This has an area of 2. This has an area of 1, but then you could also go like here, and that has an area of 2. And so in this case, the largest area is up here, and it's this list block right here. And so that's our largest area. And so what I did to find that is we have our our list, our stack, our array of areas or of heights. And then I go in and I look for the next smallest one, right? So let's just say I'm here, right? We go here, not smaller, not smaller, same height still, but not smaller. Keep going. We go all the way to the end. So we know that we have this is a valid rectangle, right? This is our rectangle right here. Going forward and backwards, there's nothing this way. So that's just that. This next one going forward, we go over here and here, this is smaller. So then we know that. And then also going this way, this one's also smaller. So then for this one, we build this rectangle right here. And then for this one, go forward, smaller. All right, so we stop there. But then over here, we have another one that's bigger, and then it's smaller. So then we have this rectangle right here. And a lot of lines here, right? We have this rectangle right here. And so we go through and we grab all these values and build up our rectangles. And so, as I literally copied the code from last one. It puts 0 in for if it doesn't find one. So then I go and replace those when I'm adding up all the areas, find the greatest area, and replace those with, the distance to the end. So, and then I go through and in this bottom one here, we get, I add up all the, I calculate each area and compare it to a max, and then I return the max I get. So
Cool. Nice. That makes sense, everyone. Any questions for Mitchell?
where's the stack going to look like?
So the stack so I literally copied and pasted the code from the last problem, the temperature problem.
Sure.
So I mean, I modified it a little bit. So that code gets the next value that's it gets if we represent that problem in rectangles, right? These are the same height. It goes here, looks here, looks here, looks here, and then it stops here when it gets greater. I just flip that around and it looks for the next smallest. Because obviously we can't do this rectangle right here because this doesn't exist right there. So you go both directions, and so it is a little bit inefficient because it is like you just have a line of one height, right? It checks every single one. So that's a bit inefficient, but it's kind of brute forcey a little bit. And it kind of checks all the. I guess it's a brute force 3D algorithm, I guess. You know, it checks the best possible rectangle for each height. So it, you know, that's exactly what it is. It's a greedy algorithm. It for each bar, for each height, it finds the biggest possible rectangle that can be there. You know, at a height 5, at the height 5, the biggest possible rectangle at a height 5 at this point is that, right? It can't go over here, right? So that's, and this one, let's just say this was for whatever reason, height 2 was. We don't care about looking at height 2 because we have one that's right height 2 right here that we can look at that area then, right? So we don't care that there's could be ones that are smaller height at this point, because if they were available, they're constricted. They're already constricted by this one right here. So yeah, so it's greedy algorithm actually.
So they're constricted by the smallest rectangle, right? Yeah. Nice. Cool, thank you for drawing that out. I think that definitely helps us see it.
Runtime space.
Yeah. So space is whatever that one is. That not great. Whatever it is, whatever the last one was, basically. And I think you said that was n.
Yeah.
Yeah. So it is. That's what it is, linear, but it's linear times 2 or 3, whatever it is. Yeah, 3 again. Space complexity also 2n. So n
For runtime.
or no, for space complexity also, because we have to store 2 arrays.
Wouldn't the runtime be if the general idea of your solution is looking for the biggest rectangle, which small rectangle is a part of it? If we have a array of all the same size, like you said, 1, would it be quadratic?
Well, no, actually, because we find the next biggest one. The temperature one is n, right? You agree with that, right?
Yeah.
So I basically, I go through once, and look all the way through, find the next smallest, and then I do it again, but I go backwards the other way to find the previous smallest. So that's 2n, right? So now we have a list of the next smallest for each height, for each rectangle, for each value for each height, and then the next smallest one for each height. So that's 2n. And then we just have to go in and take that height and the width we got from that, from the previous smallest to the next smallest, right? And you have that rectangle there. Just, that's a time to be, you get the area, and that reach the bottom. I don't know if that makes sense.
But if you do that n times, like quadratic, because you have to find.
We only have to find the next smallest and the previous smallest for each one, right?
Yeah, it should be n. You do that n times.
And we already did that, and we decided that in the daily temperatures that was n to find them, right? Going through finding the next biggest one for each one was n.
Well, I believe it's because of the way that the stack is. You'll never push something to the stack twice. So at the maximum, you can only push an item to the stack once, which would be n.
Exactly, and I use that same code to find the next smallest.
But don't you try to find the next smallest at every iterative very small triangle or rectangle?
Well, we do. Again, I'm using the same code, right? So I'm not, on this one, I'm not looking at here. I'm only looking at this top one, right? Find the next smallest one, right? I'm not necessarily you're looking at every height, because all these smaller heights, if they are, that means there's a constraint, and they're already constrained by a smaller one that's going to check them.
What I'm saying is that if we assume all the heights are the same,
Yes.
wouldn't you be repeating the temperature problem n times, once for every small rectangle?
No, so I repeat it twice. The next small, we decide, because the daily temperature problem, it gets the next greatest temperature for every single one in the stack. So it's not just the first one, it's for every single index, it finds the next greatest one, right? And so that was n, right?
Sure.
And so assuming that's n, I use the same logic, the same process, the monocratic stack. What is it?
It's a monotonic.
Monotonic stack. But instead of find the next greatest up on the next smallest.
So could you show me a demonstration of this, just like given that, like if that was your input, what would it look like?
Yeah, so. Assuming a bunch of heights that are all exactly the same. Here, it checks, goes all the way to the end, whatever. All the way to the end, all the way to the end, all the way to the end, and then it goes all the way to the end, 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 right? And that is what we were doing for the greatest temperature tree, right?
But the distinction I think with the greatest temperature is that we go to from one point in the array to the end, but we only do that once. What here I think was happening is that you cover the entire array n times. So if we assume we have our input is size 10, and all of them are the same height, we get a rectangle that's width 10 and whatever the height is for the first iteration. Then we iterate again, it's the same height or same width for the second iteration, so on, so on. So in that situation, you get quadratic runtime.
Well, I mean, I guess the thing is, again, I guess I'm not sure. I'm using the same exact code that the daily temperature problem is using.
The problem is that you're using it, I believe.
The daily temperature problem, it doesn't matter if you look for next greatest temperature or the next smallest temperature, it's going to be still the same logic goes behind it, right? Imagine if you took all the values for the greatest temperature and times them by -1, you would get that solution, right?
Okay, and my misunderstanding lies in when do you search from right to left? Like when do you choose then what rectangle you're searching for? That's not a good way to phrase it.
I don't know, I'm not quite sure how to explain it best. I don't have a huge amount with the monocratic stacks. I guess they're governments now, I guess. But it's the same logic as I guess it's just the same logic as the next greatest temperature. Is just imagine you solve the next smallest temperature problem, right? And you do that twice because you have to do it once. You run through it once. I do it once to get the next greatest, and I do it again, but this time reverse, so it gets the previous smaller ones. Okay. So I'm just doing I copied and pasted daily temperatures twice. Okay. And I changed the few things that need to be changed on it. So I'm not explaining it the best, but that's I guess how I can explain it, I guess.
Yeah, no, thank you for coming up and drawing it all out. I think that helped me visualize your code and everything. Yeah, cool. Alrighty. So next, that's all the weekly problems for stack this week. Next, let's go through and figure out what problems we want to do for next week. So I was thinking we would do this. So we do tree for next week.
Can we do trees the other week?
I don't think we've done trees yet. We did linked lists the week before last. Yeah,
it was linked list. That's right.
Yeah, so just following the roadmap here, we've done 2 pointers, did stack, sliding window, linked list, binary search. Almost to the end. We're on to trees now. So we'll pick a couple easies. This is so annoying, the zoom overlay. Go over there. Too many tabs. Okay. Inverted binary tree. I think that's a good one. Yeah, we got to do that. Okay, so we'll do inverted binary tree. Subtree of another tree. If anyone has any suggestions for tree problems they like?
I don't like trees.
I don't like trees either, to be honest.
Trees, symmetrical trees, one, I don't know if it's a medium,
Symmetrical tree.
I don't know what the exact problem is.
Oh, yeah, I
If you
forgot.
want- if you want-
Yeah, what's it called? Might be on neat code. Let's go line 75.
Tree.
Yeah, but I like that one though. It's like, I can't remember the name of it. Got invert binary tree, subtree of another tree. Sure, let's do that. And metric.
There, we have some too, I did this one once at some point.
It's easy. Maybe we do two easies, a medium, and an optional hard.
Paths, I think it was a pretty easy medium.
So could do,
I like that one, yeah.
yeah, do that for our hards. That'll be like our paths. Invert, symmetric. That. Okay. Medium some two.
An easy medium, I'd say.
Okay, I'll post that at the end of our meeting. And then let's go through a tree problem together, maybe get like a little intro into trees. Come on. Recursion is not fun to learn. Huh?
Did you assign max with that? Or do you want to do max with that?
I did not assign that. Let's do it.
I think it's the second one.
Yeah. So definitely fine. I haven't done trees in so long.
Can't get rest.
Wise man. Where do trees do? Stuff like autocomplete. It's there, especially in patterns like networks. Yeah, lots of different things trees I've used before. I've used a tree to represent logical statements, represent logical equations. I've used that before. Automation. No, not quite. I suppose you could use it for automation, but I was just writing out a logic calculator, and I used a binary tree actually to represent logical statements. So I had comparison nodes, and then I had value nodes. So
Nice. So I don't think I've ever like used a tree other than for lead coding, getting a job and job interviews. That's a big one.
it has uses, unfortunately.
Unfortunate.
It's gotta be good to know though, come on now. Yeah.
You gotta learn them.
Yeah.
All right, so given the root of a binary tree, we want to return its maximum depth. And a binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So see if we count here, 1, 2, 3, or we could do 1, 2, 3. Our depth, our maximum depth is 3, and there's 2 paths that we can use to get there.
I suppose the other thing about trees is that they're kind of almost a precursor to graphs, which do have even more uses.
Yeah, graphs are a bit more complex.
Graph, yeah, it's kind of like linked lists, trees, and graphs.
Yeah, it's exactly I think how the roadmap is laid out.
And then you gotta write Google Maps.
All right, so any ideas for what kind of traversal method we want to use to get the maximum depth?
Yeah, there's a recursion.
Recursion, there's
Fine.
I can go over all the, we probably wouldn't have time for that. Like in order, pre-order, post-order,
Yeah, all those things I forget.
all those things, those good things. So I'm thinking we want to do a DFS type of algorithm as opposed to BFS. So what a DFS algorithm would do is it would start at the root node and visit all of the left child's nodes. And then we visit the root node, and then we visit all of the right child nodes.
It doesn't necessarily matter a ton, I guess.
Yeah,
You have to check all of it anyways.
that's true. So let's have, thinking we're going to do this the recursive way. So I want a helper function. Let's see. Recurse. Let's first get our base case. So our base case is when we want to return from our recursion tree and go back up. Yeah. So a node, not node, then we're going to return. Otherwise, you want to keep track of what level we're on. So maybe we have another parameter called like level. And each time we call recurse, we're going to increase level. So first we want to check if the child node does exist. So like say we were at 9 is our current node. We aren't able to recurse down to its left or right subchild because they don't exist. So we first want to make sure that they exist.
You don't always do that.
That's true. Yeah, we just return automatically. So recurse.
So is it more efficient because technically it doesn't have to add anything to the program stack?
That's true. It would be slightly like more efficient.
I think you're gonna run into null pipeline there with the edge case that they give you a null root. Depends if you want to check whether it's null before you
We do both.
Yeah, do both.
Or you have two helper functions. I mean,
Okay.
I mean, it would actually be mildly helpful. It would actually be mildly helpful because if you use one helper function, you do have to put in one no matter what. So if you get two, you can hide that one because that one is mandatory.
Yeah, that's true.
So in terms of like thinking of good implementation, it might be technically better of two depth layer of helper functions.
Two depth, like two different helper functions that.
Yeah. Or I suppose, yeah, I don't know. Yeah. Actually, suppose we do have max depth in the helper, yeah. I don't know.
Okay, so what we want to pass when we first call this function for the first time is root, which will be our current node. And then our level will start out as 1. You guys one,
I think you start at 0.
3.
No, I did one.
I was thinking of
Well, the problem is, let's assume we have one node. So our depth would be
One.
1.
Hmm.
Once you call recurse, it's gonna add 1 to that. So you start with 0 if there's no null.
Well, no, it doesn't have one.
return.
We just return level.
Well, no,
Level
we
minus
don't
one.
check the children. And so we're gonna, if
If not,
not,
it doesn't. I don't know what I have.
0.
So we want to return level here. Oh, is Daryl wanting to share?
was trying to possess you.
Whoa. I didn't know you could do that.
So what were you guys saying about it not being so?
What were you guys saying?
I see what I was just saying, that since we just returned level, we don't need to worry about that. I was saying we might be off by one by adding one too many to level. But I was wrong, so you don't need to worry about that.
I'll just let Daryl take over from yours.
It's possible. Zoom is Daryl's possessing him. He's possessed by a ghost right now. I must be misunderstanding something. This man is controlling your entire computer.
He can do whatever he wants now. It's
Yeah.
kind of.
And find his homework file. I'm about to say, there's no way. I did not know you could do that. How would they have set that up?
He's missing the cult or the.
If you look at the top part, Daryl, you
Yes,
guys controlling your
There it
screen.
is. Oh, he's also missing.
Well, I mean, it's the same way you can say images, you can send controls. What? I mean, if you have like, if you know, you can have like a macro that does something with your mouse. Same way Zoom can do in this, Zoom can go move your mouse here, input this character.
Okay, nice. Thank you,
Bad.
Daryl.
What?
Yeah, I'm a bit rusty on trees for sure.
This is why Skype ain't used.
Terms of nodes, then we just increase each time we visit a new node and we return the maximum of that.
Should make it a one line. It'll be too hard. Okay.
Daryl's gonna take over and not allow us to do a one-liner. Okay, nice, cool.
Is there anything else about that, or is it just? One return max, just so.
Yeah, that's why I just, it's like whatever the max of the levels. Right after.
I think that's a good solution, but maybe not the best beginner solution, because it's a little bit. Not super hidden, but a little bit hidden in what it's doing almost.
You're right, you shouldn't make that one liner.
Exactly. One line, it's so much easier to read than multiple lines, right?
Yeah.
Bigger person, they get tired of like one or two lines,
Yeah.
You just need to put everything on a single line.
I mean,
I don't
He's
think anyone would
suspicious.
come back to our meeting if we did
I'm
that.
starting to suspect that that wouldn't work that way.
I don't know.
I'll strike the entire. Even have the numbers on the left, you just have like a really long scroll bar that goes right in.
All right.
There's also a new vertical, did you know?
Nice.
I don't think it'll run.
I think that's it for today's meeting. We probably don't have time to go through another one. I think so. We got 7 minutes.
Speed run.
What was that? Oh, big O. So we're gonna go through every node in the tree. So big O is O N. And then we aren't using any data structures here. So it's going to be constant for space complexity as well. Oh, we got the call stack. So every time we call, we're going to be placing a function. Every time we do self.max depth or self root left or root right, we're placing a function call onto the stack. So its time complexity is also O of n, where n is the number of nodes. Yeah.
Yep. Sweet.
Right. I think that's it for today's meeting. Thank you everyone for coming. If there are any more questions, let me know. You all good? Yeah,
Looks like you're not quite getting the space complexity part.
all right. Sweet. I'll see you all later. Thank you everyone for coming.
Yeah,
Bye.
I mean, so the space complexity, the time complexity is, how many sets of how many operations does it have to do, or how many, well, not operations, sets of operations it have to do.
Yeah.
So it has to, since I have to check every node, you have n nodes, therefore time is n. And the
Yeah.
space, it's the worst, we kind of have to check the worst case for the complexities.
Yeah.
So,
And so imagine everything's on the left, like just on everything on the left node, if we had n nodes, have to, you have a program stack, each time you recurse, we have to add a new thing in the program stack, which takes up space. And so we'd have to go n times, so then therefore that's what our space is.
Right. I don't know like, yeah, the difference between the, we go to,
Yeah.
how do you say, we go notations.
Yeah,